Most of us will just correlate chemical engineering is similar to chemistry major. But, do they serve the same purpose? Well, chemistry major works in micro scale, yet chemical engineering dominantly works in macro scale. Chemistry is a part of chemical engineering, but they are a totally different major. Then, what do chemical engineers do? Chemical engineers are responsible to convert raw materials to some kind of product which values more. Along the way, chemical engineers will be faced with process designing, process controlling, and process development. On the other hand, it's also chemical engineers' duty to concern about the process effect to the safety of an environment. Besides of producing and transforming materials, chemical engineers also take care of materials transportation within process units. With the ability that chemical engineers are capable of, chemical engineers are required in petrochemicals, food industries, pharmaceuticals, environment control, and biotechnology industries. Find out more about us on our website at www.ikitbsi.com.
PT Pembangkitan Jawa Bali, anak perusahaan dari PT PLN, hadir untuk memberikan energi kehidupan melalui bidang usaha pembangkitan tenaga listrik. Dalam menjalankan perannya, PJB selalu berupaya untuk menjadi terdepan dan terpercaya dalam bisnis energi berkelanjutan di Asia Tenggara. Dari Indonesia dan untuk dunia, semangat kami tercipta untuk Anda.
Most of us who just correlate chemical engineering is similar to chemistry major. But, do they serve the same purpose? Well, chemistry major works in micro scale, yet chemical engineering dominantly works in macro scale. Chemistry is a part of chemical engineering, but they are a totally different major. Then, what do chemical engineers do? Chemical engineers are responsible to convert raw materials to some kind of product which values more. Along the way, chemical engineers will be faced with process designing, process controlling, and process development. On the other hand, it's also chemical engineers' duty to concern about the process effect to the safety of an environment. Besides of producing and transforming materials, chemical engineers also take care of materials transportation within process units. With the ability that chemical engineers are capable of, chemical engineers are required in petrochemicals, food industries, pharmaceuticals, environment control, and biotechnology industries. Find out more about us on our website at www.ikitbsi.com.
PT Pembangkitan Jawa Bali, anak perusahaan dari PT PLN, hadir untuk memberikan energi kehidupan melalui bidang usaha pembangkitan tenaga listrik. Dalam menjalankan perannya, PJB selalu berupaya untuk menjadi terdepan dan terpercaya dalam bisnis energi berkelanjutan di Asia Tenggara. Dari Indonesia dan untuk dunia, semangat kami tercipta untuk Anda.
I would like to welcome all of you engineering enthusiasts to the AISChat X ChEminar, Achieving Low Carbon Future Using Carbon Capture Technology. I'm Alia from Industrial Engineering ITB as your MC of today's AISChat. I'm very glad to meet all of you today. First of all, we'd like to thank all of the attendees to have come here and participate in this event with your full enthusiasm. We'd also like to thank our sponsors, PT Pembangkitan Jawa Bali and PT Energy Management Indonesia, and to our community partners, WRI and OPA. And last but not least, we'd like to thank all of our media partners that helped us make this webinar come true. Thank you for your collaboration with us. So before we start our discussion today, there are several rules that has to be met. We have sent the rules through the WhatsApp group, so please kindly read the rules carefully. And in the screen here, you can also read the rules here. And we expect that these rules must be met by all of us here. As for today's agenda, you can see it in our rundown. So here is the agenda for today's AISChat. You can see here we will be starting with the opening, and then some sessions, and then also panel discussion before finally the closing. For the panel discussion, the duration will be quite longer, so we encourage you to think critically and prepare your burning questions to our amazing panelists here, Dr. Anna Kituhon and Dr. Joris Kornev, so that we can explore all of the sustainability industry together. Before proceeding to session 1, I would like to tell you more about AISChat. So AISChat is a student chapter originated from IQ Global and the first ever IQ student chapter in Indonesia. Besides in ITB, there are also AISCI in 10 November Institute of Technology, in Pertamina University, and also in University of Indonesia. The goal of ITB-SE is to empower and enable students to have the best foundation to fulfill a career in the chemical engineering industry by various programs. The ChEminar that is collaborating with AISChat today is one of ITB-SE that is aimed to enhance the hard skills in chemical engineering. Now let's talk about AISCE. So what is AISCE 2021? AISCE is a regional student conference with the scope of Southeast Asia that is held by the IKE Student Conference Indonesia. In AISCE 2021, there are several events that we are going to hold. The first one is the pre-event. The AISChat today is one of the pre-event of AISCE, so stay updated on our Instagram because we have so much more, many more in the future. So stay tuned, guys. And besides AISChat as the pre-events, there are also other pre-events like AIC careers, and also we have competitions. Right here we are going to hold the poster and paper competitions, and you can register yourself to these competitions starting from now. So go check our Instagram for more information regarding that. Besides the pre-events and the competitions, there will also be a sharing and social night. In this social night, you can network and connect to so many people internationally or like from other institutions to make meaningful connections and share from one another. And also, last but not least, there's the conference day. So in AISCE Conference Day, you will go through various experiences in the emerging topic of sustainability. The AISCE grand theme this year is Sustainability in the Industry, Igniting Ideas Through the Spirit of Youth. The purpose of today's AISChat is to introduce sustainability to you, so stay tuned for the other AISChat series. As I've said before, today's discussion will have the specific topic of achieving low carbon future through carbon capture technology. So to get the discussion going, there will be our amazing panelists here. And to start, let me introduce you to our moderator of the day that will moderate today's session, Mr. Anggit Raksejati.
Okay, good afternoon, everyone.
Hello, Mr. Anggit.
Hello, good afternoon.
So, Mr. Anggit here is a lecturer in chemical engineering major in ITB, and he is also the COE of CCS CCUS Indonesia. So, without further ado, please welcome Mr. Anggit Raksajati.
Okay, everyone. So my name is Anggit Raksajati. I will be the moderator for today's webinar. And I'm a lecturer in chemical engineering ITB, and also I'm a secretary from the Center of Excellence in Carbon Capture and Storage and Carbon Capture Utilization and Storage in Indonesia, which is founded around 3 to 4 years ago, since 2017. And let's use this opportunity for us to learn more about the CCS and CCUS technology, which would be one of the important technology for us to be able to meet the CO2 emission reduction. So, yeah, I'm looking forward for the discussion. Okay, so I would also like to invite you to join this event, which is arranged by ITB, starting from tomorrow. So I will send the link for the registration in the chat column. This is for final year bachelor degree student, master, and even PhD. If you want to learn more about the whole CCS chain, you can join this 10 days program starting from tomorrow. You will learn about the capture part, the transport part, the storage part, and even the social aspect of CCS. And we have a lot of speakers from the ITB and also from international speakers. You can check in the website. And it's arranged by our national and international partners, including the IAGHG. Okay, so we still have a lot of spaces if you want to join these virtual classes starting from tomorrow. So please check if you're interested. Okay, let me go back to the slide again. So for the speakers, we have 2 speakers. The first session will be with Dr. Arne Katelhoen, which is a co-founder in Carbon Minds. He will talk about mainly the CCUS in industrial sectors. And he also currently a life cycle assessment team leader at Institute of Technical Thermodynamics in Aachen, Germany, and visiting scholar at Brand School of Environmental Science and Management, and also project development of clean development mechanism at UPM Environment Project Management. And then the second speaker would be Dr. Joris Kornief, who is a strategy consultant in sustainable geoenergy. And he's also a scientific coordinator in the North Sea Energy Lead Task Force in the thermal energy storage of the European Associate for Storage of Energy. And he's also the lead author of IAGHG report on the global potential for biomass with carbon capture and storage. So please use this opportunity to learn about how we can combine the application of CCS with the biomass, as we know that Indonesia has a lot of biomass resources and potential, including the palm oil industry. So we can explore this session, including the discussion session, to get the insight. How can we use these 2 concepts or two sectors together? And if you have any questions, you can write it in the slido.com. So you just need to scan this QR code or enter the code, and then you just need to type your question. It will be better if you can specifically aim if the question is intended for Dr. Cornif or Dr. Katalhun. So we will have time around 1 hour at the end of this webinar to talk about this panel discussion. Okay, so I think this is the closing. If at the end of the session, please fill the feedback before 8th of November, and the feedback link can be accessed through this website. And the password is carbon-future-3. Okay, so I think that's it, the introduction from me. So any other information from the committee before we invite our first speaker? Okay, so I think we can now invite our first speaker. Please welcome Dr. Arne Katalhun, which will present the industrial sector of CCUS implementation. Okay, well, thank you for joining us.
Yeah, thank you very much for the kind introduction. Yeah, it's a great honor for me to be here and speak here in front of this audience. So let me try to share my screen first so that you can see my presentation. So I hope you can see my presentation now. My name is Arne Katalhun. I'm from Carbon Mines. And today I'm speaking on behalf, of course, of myself and also of a number of interesting co-authors. I did this work together with Raul Mais from Aachen University and Carbon Mines, and Sarah Deutz with Sangwon Soo from the University of California in Santa Barbara, and André Bado from ETH Zurich in Switzerland. And the topic of my presentation is climate change mitigation potential of a very new type of technology, of carbon capture and utilization technology. And we will have a look into how much greenhouse gas emissions we can save specifically in the chemical industry. And in order to understand this change in having the chemical industry, it's always good to start with how the situation looks now, to start with a status quo in the chemical industry. And now you should see a slight change. So if something technical is not working, let me know, please. So today, the chemical industry is almost exclusively based on fossil feedstocks. About 58% of this fossil feedstock is used as a carbon feedstock for the chemicals and plastics that we're using. So this is basically the material that gets directly incorporated in the products that you have in your hands. For example, the keyboard of the computer that you probably have in your hands right now. The rest of this energy is used as process energy, so to heat the processes to generate the heat that you need. And of course, this use of fossil feedstock and fossil fuels causes quite a lot of emissions, about 1.5 gigatons of CO2 equivalent emissions for the global production of chemicals and plastics. But that's not even it, because these chemicals, they will also be used, for example, in the products that we have. And after we used our products, we dispose them. This often happens in a waste incineration plant. And of course, the burning of these fuels causes additional emissions. So the life cycle emissions are a bit higher compared to only the production emissions. So what we see here, and what is the industry about today, it's basically a flow from our fossil resources, from the ground, through our production, through the use, through the disposal, right into the atmosphere. So there's a almost linear flow of carbon atoms from the ground in the atmosphere. And this is a huge problem that we're facing. This is what causes the climate problem. So let's think about how we can change this situation. So the idea is we need to avoid this flow of fossil resources from the ground, and we can do this by creating more circular carbon flows. And one option here is carbon capture and utilization. or shortened CCU. And in carbon capture and utilization, we capture CO2 from emission sources. This could be a power plant, this could be a waste incineration plant, or even directly from air. And we use the CO2 as a carbon feedstock for the chemicals that we are producing. So we basically recycle them and put them back into the production chain. And we can do this by using renewable energy. So CO2 is very low in energy. To build products out of this, we need energy. This could be another high energy reactant, often hydrogen, and we can produce this using renewable energy. So the question is, what is the climate change mitigation potential of this concept of CCU? And in order to understand this question, we need to address another question first. How would the chemical industry actually look like if it were entirely based on carbon capture and utilization? What you see here is how the chemical industry looks like today. So on the bottom of the slide, you see the feedstocks, crude oil, natural gas. Those will be transformed in a number of platform chemicals. And these platform chemicals are further transformed into all the chemicals and plastics products that we know today. So it's basically a little bit of a structure of a tree. What is important to say is that this picture, even though it looks quite complex, it's still extremely simplified. So the chemical industry is a highly interdependent production network. Why is that? Well, we cluster plants in order to exploit potentials of energy integration, or we utilize the co-products of plants and other plants. So this is why different plants in the chemical industry are interdependent. So if we want to understand changes in the chemical industry, we can't look into different chemicals or different plants one by one. No, we need to capture this complexity of the industry. We need a detailed model of the chemical industry to understand potential changes. And in this work, we built such a detailed model of this part of the chemical industry down there for the production of so-called large volume chemicals, so the biggest chemicals in the chemical industry. What is interesting about these 20 large volume chemicals that we are looking at is, even though we have thousands of chemical products, those 20 large volume chemicals, they account for about 75% of the entire CO2 emissions associated with the global chemical industry. So if we get the modeling of these chemicals right, we already have a quite good indicator for the entire industry. And we do this in this study by looking into the best available fossil-based technologies and compare them to alternative options based on carbon capture and utilization. So how can we do that? Well, when we started to build this model, the first thing is we had to understand how these supply chains worked. So we looked into the supply chain. For every single production steps, we developed very detailed process flow sheets, like the one that you see on this slide, based on an industrially validated database. We used these flow sheets in order to extract mass balances, energy balances, and the direct greenhouse gas emissions of each process. And based on this information, again, we could build what is called a bottom-up model, so a detailed model of the this part of the chemical industry, consisting of more than 160 processes. And this model now allows us to track the flows of energy and material throughout the entire production chain of the chemical industry, from the resources to the products that we're looking at. Yeah, so it's basically a digital representation of how chemicals are produced today. And once we have this type of model, we can now, let's say, play with it. And we did it by transforming it into an optimization model, which can minimize the greenhouse gas emissions of the production of these 20 chemicals for the final demand in 2030. And the constraint here is that we will produce enough chemicals to satisfy the expected demand for 2030. And based on this model, we now compare 3 different scenarios. And the first scenario is our baseline. So it's what we call the business as usual scenario, or the conventional scenario, where chemicals are produced like they are produced right now. So let me show you how this works. So basically, first of all, we input the final demand of all the chemicals into the model. And these are just groups. So those are into the types of chemicals. So those are the 20 chemicals that you see here. Then we allow the model to use only the feedstocks that are used in the industry today. And then we can run this optimization model. And this model gives us an entire structure of the chemical industry based on this optimization approach. And here in the baseline scenario, we see again that fossil resources are transformed into platform chemicals, olefins, ethylene, propylene, and aromatics, BTX. And those are again the platform for the other chemicals that we have in our system boundaries. So what you see here is just a more detailed representation of this part of the chemical industry down there. We also calculated the emissions, which is in line with other emission expectations for 2030. So this was basically the validation of our model. It seems to work. And now that the model works, we can go a step further and now allow the optimization model to choose not only the fossil resources, but also CO2 as a carbon feedstock, the captured CO2 from CO2 utilization, and we allow the model to use hydrogen from water electrolysis, so hydrogen which has been generated based on electricity. And we do exactly the same. We built two scenarios. A first scenario, which we call the high TRL scenario. TRL stands for technology readiness level, and high TRLs stand for technologies which are developed already very far, which are very close to the market or already in the market. We do the same. We input the same final demand as in the previous slide, but now we allow the model to use CO2 and hydrogen as a carbon feedstock. We implement these high TRL CCU technologies, which is the production of methanol, huge chemical, platform chemical, from CO2 and hydrogen and methane. And then we run the model again and get an entirely new superstructure or structure of the chemical industry. And what you see here is how the chemical industry would look like if it were entirely based on CO2 and hydrogen. So here, CO2 and hydrogen are transformed into methanol and methane. We use so-called methanol to olefin and methanol to aromatics processes to end up with ethylene and propylene, which are again the basis for the other chemicals. There are two things that are very interesting in this slide. The first one is, as you might have seen, I've changed the scaling of the slide. And this is because we have a very large co-production of water, so otherwise it just wouldn't have fit on the screen. So the production of methanol and methane, and also the methanol to olefin processes, we co-produce a lot of water. We can recycle this, of course, for hydrogen production, but this means that our plants must become much bigger, and this will increase investment costs. But there's also the good news in this, the part of the chemical industry that you see back here. This is the same structure that you saw on the previous slide. So it's the same plants, how we start with ethylene, propylene, and aromatics and add up with the final products. So here, not much investment would be needed. So this is one scenario how a CCU could be implemented. But we also built another scenario because there are quite many CCU technologies which are not at high technology readiness level, which are not very far in the development, but are more ideas and research. In the second scenario, we included these very new technologies. So in addition to CO2-based production of methanol and methane, we included processes that, based on CO2 and hydrogen, can produce ethylene, propylene, BTX, carbon monoxide, ethylene oxide, and styrene with direct CCU routes. We do the same. We start with CO2 and hydrogen. We can run the model and again end up with a completely new structure for the chemical industry. And here the good news is a little bit less water is co-produced. This is an indicator for higher efficiency. But at the same time, this part on the right side here, this is a completely new superstructure, so it already hints that there would be quite a lot of new investment involved in achieving this scenario. But again, this is a structure how the chemical industry or how a renewable chemical industry based on CO2 and hydrogen could look like. And this is basically also the answer of the first question. So what would the structure of the chemical industry would look like? So once we have this, we can now go a step further and look into the greenhouse gas emissions. So on this slide, on the vertical axis, you see the cradle-to-grave greenhouse gas emissions of the chemical industry, of the entire chemical industry, which is in the system boundaries, so the 20 large volume chemicals from cradle to grave. On the horizontal axis, you see the greenhouse gas emissions associated to the production of electricity, because we remember we used hydrogen, which has been generated based on electricity. So how electricity is produced is very likely to matter. So let's have a look how important this is. This is first the conventional scenario. This time about 4.5 gigatons of greenhouse gas emissions per year. It's higher than in the first slide because it's cradle to grave and because there will be an increase in demand. So about half of it is due to the production of chemicals, the other half for the end of life. Here we assume the incineration. And this is the result for the high TRL scenario. So what we can see here already is that CCU has a very large climate impact reduction potential, about 3.4 gigatons, so we can bring the industry very close to zero in this scenario. And this reduction potential is even higher for the low TRL scenario, for the scenario with the new CCU technologies, 3.5 gigatons per year. So great news, CCU can have a large impact on the climate. But there's also other things that we see in this diagram. First of all, there's a range shown here. Why is this the case? Well, the range indicates scenarios where we capture CO2 from different sources. I told you that we can capture this from industrial sources. Those may have a very high concentration in CO2, which means we need less energy to capture it. So it's a better case for the emissions. But we could also capture it from air. So it costs a little bit more energy. So in most scenarios, this is the upper range if we don't have like extremely clean energy. So this is why we have these ranges here. But even more importantly, we can see that we can only achieve high climate impact reductions if we have very clean energy, clean electricity for hydrogen production. And this is the horizontal axis. So we need electricity with a carbon footprint that is lower than 100 grams per CO2 equivalent per kilowatt hour, but even lower, maybe half of it, 50 or lower. What does it mean? Well, what you see here is a carbon footprint of countries which already have an extremely low carbon footprint. So Germany would be right on the left of the picture here. Austria, Switzerland, a lot of hydro, Belgium, France, nuclear. But to get to the very low carbon footprints, we really need the renewable energy like solar PV and wind electricity. So we need to be able to generate low carbon electricity at a very large scale to achieve the scenarios. And this sounds quite difficult because having renewable energy is a huge aim, and the expansion of the renewable energy system, of course, takes time. So the big question here is, how much renewable energy do we need for carbon capture and utilization? To answer this question, I brought this different diagram here. On the vertical axis, again, you see the cradle to grave greenhouse gas emissions of the chemical industry. On the horizontal axis, we now see the electricity, the additional electricity that we can give to the chemical industry for carbon capture and utilization. We have our fossil benchmark, which doesn't need any more electricity than it has right now. And here we see the results for the low for the low TRL scenario. So basically, the greenhouse gas emissions in relation to the amount of electricity that we can deliver to the chemical industry, and also depending on the carbon footprint of electricity. And those are these colorful numbers here of the electricity that we can give to the chemical industry. This is the amount of electricity that we would need to achieve the full greenhouse gas emission reductions that we can, which is down here. It's about, it's 80.1 petawatt hours. When I saw this number, I didn't have much of an idea what this means. So what does it mean? What you see here is a global renewable energy target according to the International Energy Agency Sustainable Development Scenario for 2030. So in this more ambitious scenario, it's a total amount of renewable energy that we would need for the entire world. So this means the demand for CCU would be even 20% higher compared to what we expect to have for all other sectors together. So those are incredibly large amounts of renewable energy that we would need for these scenarios. And it's even more for the high TL scenarios. So these new technologies at the low development stage, they are quite promising. But there's also, again, a good news in there. There are differences in efficiency in reducing the climate impact or in using renewable energy to reduce the climate impact. You can see this because the slope of this diagram in the beginning is a bit steeper compared to later. So this is a higher efficiency. So if we can't deliver enough renewable energy to the chemical industry right away, for example, in 2030, we can at least use it for the most efficient technologies, so the ones that use the renewable electricity most efficiently to reduce climate impact. But still, only if we go for an implementation of 10%, 20%, 30%, this will be still large amounts of renewable energy. So as a society, we need to think about it. Do we want to give our precious and limited renewable energy to the chemical industry, or are there better uses for renewable energy? And to answer this question, I transformed the slide a little bit and added these few lines. And those few lines indicate the emission reductions that we could achieve by not giving the renewable electricity to the chemical industry, but by putting it into other sectors, for example, into heat pumps, in order to substitute natural gas boilers. And we can see this would give a much higher emission reduction per kilogram used. So we could get down here only with 5 petawatt hours compared to 18.1. And we also have a higher efficiency for e-mobility, electric cars to substitute gasoline or diesel cars. And even for simple electro boilers, so it's basically like the water boiler that you have in your kitchen, just on a industrial scale, to substitute natural gas boilers. So we can see that those large-scale energy users, they reduce more emissions per kilowatt hours. So from a societal point of view, those should be prioritized as long as there's no other solutions found for them. So we can summarize. There's a large contribution for climate change mitigation possible for CCU, but only where or when more efficient renewable energy uses are unavailable. So we don't steal the renewable energy from more efficient options, so that we can use unused renewable energy resources. Sounds bad, like a small niche, but let's have a look at where we have renewable energy potential in the world. And this slide shows you the amount of renewable electricity that we could, or energy that we could generate if we fully exploit all technologies that we use. So this is basically the upper bound given by nature, and the demonstrated technologies. And what we can see here, I'm in Europe right now, for example, the potential is tiny. Yeah, so in Southeast Asia, it's with got it here. So there's a bit higher potential there, but the huge potentials there on the south half of the planet. We have Australia, we have Africa, we've got South America, and here we have partly areas which are not very densely populated. So, for example, the desert in Australia. And there we don't have electric cars. We don't need heat pumps. So basically there we have huge renewable energy potentials that do not compete with more efficient technologies. So if we could exploit these renewable energies, for example, by producing methanol there, which we could bring to the industrial areas for further processing, we could enable an international trade of renewable energy, and by this means make the chemical industry much more efficient. So there's a high potential in remote areas with currently untapped renewable energy resources. And this is also one of the main messages that I would like to give in my presentation. So let me conclude this presentation. What I would like you to remember from this talk are a few things. First of all, that carbon capture and utilization has a very large climate impact reduction potential in the chemical industry, 3.5 gigaton CO2 equivalent by 2030. But to exploit this potential, we need very large amount of low carbon electricity. It's a bit higher for the currently demonstrated technologies. We expect to be able to bring it down quite a lot with new developments. So CCU research, carbon capture and utilization research, is very likely to improve the energy demand very substantially, but it will stay very high. We've shown that carbon capture and utilization uses renewable electricity less efficiently for CO2 mitigation compared to e-mobility and power-to-heat applications. And this also goes for carbon capture and storage, where we will have a look in later in the presentation, if I'm right. So as long as we can need the renewable energy for a better, more efficient application, we should do this. But still, there's a huge potential when we have decarbonized these other sectors, because we will still need material for our chemical industry. And there's a huge potential in areas where we have a lot of renewable energy, so there are untapped renewable energy resources. So, and this is also my last conclusion from the slide. So thank you very much for your attention. And yeah, I'm looking forward to your questions in the panel discussion later.
Okay, thank you very much, Dr. Katolhun, for the presentation. I think we will have a separate session for the question and answer at the end of the second speaker. So please, for any participant, if you have any questions, write it down the question in the Slido with the code as written in the chat room. So now I would like to welcome our second speaker, Dr. Jorif Kornif, who will present about the bio-CCS. Okay, please, Dr. Kornif.
Yes, thank you very much for the kind introduction, and thank you very much for having the opportunity to speak at your very interesting conference. Indeed, I'm going to talk you through a little bit on the status of bioenergy with carbon capture and storage. You've already been introduced by Dr. Arne on CCU, so carbon capture and utilization, and I'm going to talk about also on the application of biomass in this value chain, and also the role of storage. I am from a Dutch research institute called TNO, and basically we are the bridge between science and application of the science in the industry. So we always work together with science, so with research institutes, universities, and with companies to actually bring technologies into the market. And that's also my role within TNO, to bring new technologies further ahead down to the market. And actually, just to get a little bit of blood going also in your system, I would like to ask whether you can fill in the poll that was also introduced in the, I think, in the Slido. And I'm really keen on those who are online, whether they can fill it in. And okay, that's very interesting. Can I also see how much people have answered the question? Okay. Oh, that looks good. So I think I have a little bit of a feeling now on who is that some of you have actually studied it. So that's very interesting. You can check if I'm making mistakes in my presentation. And I also consider that some of you have never heard of it. So I'm going to get you through the presentation back. Can I have the presentation on screen? Yep, thanks. So I have 4 sections in my presentation. So basically, I think it's very important to consider the why. So why do we need bio-CCS? So bioenergy combined with carbon capture and storage. How does this value chain look like? Are there already being done in the world? If we want to introduce this into the new energy system of the future, how can we do this and what's needed? So first, the first step. So why do we actually need it? And what you see in front of you is basically a very large set of future scenarios made by the IPCC, so the International Panel on Climate Change. And what you see here is a group of scenarios that bring us to a future that limits global warming below 1.5 degrees at the end of the century. And what you see also is that there are a group of scenarios called P1, or some scenarios called P1, P2, P3, and P4. And those are illustrative pathways that help us think how this future could look like. That brings us to 1.5 degrees max in 2100. And you see in almost all scenarios, the line go below 0. So that means we need negative emissions at some way, somehow. And they have given also the opportunity in these scenarios to use biomass with carbon capture and storage. So basically you capture CO2 from the air as the biomass is growing. You capture the CO2 from using this biomass in a pathway, I'm going to explain that later, and you store it in the underground. So basically you remove CO2 from the atmosphere and store it in the underground. And you see here that the potential that you need in these future scenarios is actually huge. So in 3 out of these 4 pathways, we rely on a technology called BECCS, or bioenergy with carbon capture and storage. And in the largest scenarios, we actually need 16 gigatons. So remember the quotes by the previous speaker, the gigatons per year. We need 16 gigatons per year and store it in the underground. So that means that you have to build an infrastructure and economics and market for an industry that is as big as the current oil and gas industry, but then just for CO2 transport, storage, and using it. So you need to build a whole new infrastructure that is not out there yet, and we need to build it as large as the oil and gas industry is now, just based on CO2 to get these numbers. So why do we need it? Because we need negative emissions, but it's going to be a very big challenge. So how does this BECCS value chain look like? So basically it always starts with biomass feedstock. So I've noted here a tree, but it can also be a lot of other biomass feedstock like waste from municipalities, but it can also be fast growing crops. It can be sludge waste, everything with a biomass feedstock in it. Then you have to pre-treat it. In large cases, it has to be dried or in other ways treated so that you can transport it to the area where you need it. Then in a conversion plant, you can use it. So you can use the biomass to produce heat, to produce electricity, but also to use chemical feedstocks. Use it in maybe in steel production, cement production, a lot of parts where you can use this biomass. And the CO2 that is being released by this use of the biomass is not being released into the atmosphere, but you capture it and transport it via pipelines and store it in the underground. For instance, in empty gas fields, empty oil fields, or aquifers. So there's water-bearing layers in the subsurface where you can inject the CO2 in it and that it stays there for the next millennia. So this is the basic concept. And here you can see again, you capture basically the CO2. The capturing is being done by nature, by growing biomass. And then the chemical engineers make it work in the industry or the industrial facilities to actually remove CO2 from a stream, transport it and store it in the underground. So I think as a chemical engineer, you have a very important task here, because you have to basically make sure that these industrial systems work where you capture the CO2. And there are several flavors to do this. So how can you capture CO2? You have post-combustion capture. You can capture basically CO2 out of the flue gases from a process. So let's say combustion of biomass. For that you need air and a fuel, and the outcome is a CO2 concentration in that flue gas, and there you capture the CO2 using chemical absorption. This is already a proven process since the last century. It's been invented in the 30s last year. So it's well applied already, but not so much applied yet for carbon capture and storage. Then we have pre-combustion, basically always evolves around a high partial pressure of CO2 in a flue gas or in a process stream. And here it follows from gasification of biomass. So you can gasify biomass using air or steam. And then you have a water gas shift reaction or reform reaction. And from that reaction, you can also capture CO2 most of the time using pressure swing adsorption or membranes. Or chemical absorption. So there are different means to capture that. And the main benefit of this line is that you capture CO2 at a higher partial pressure. So the cost of pre-combustion capture are mostly lower than the cost of post-combustion capture. Then there's the third flavor. It's called oxy-fuel combustion. Basically, you combust a fuel with oxygen or a very high concentration of oxygen. So you get almost a very high concentration of CO2 at the end. So in most of the technologies that are being proposed, you basically remove the impurities from the end stream, and you get a clear and pure stream of CO2 that you can store into the underground. This technology has not been used so often as the others one above, so post-combustion and pre-combustion. Then you also have industrial processes where you have like cement production or ammonia production, where you can capture the CO2 in the industrial process. I have some examples later. So how do these BECCS technologies then look like? Well, we have basically 4 groups here. So on the left-hand side of the slide, you see the biomass source that we can use. And on the right-hand side, we see the end product that it will yield for us. So first we start with the fermentation route. So basically you can use manure, so that's dung, or biodegradable waste from municipalities or other sources. And you can use it in a fermentation, so digestion, to basically produce biomethane. And from that process you can capture the CO2 and remove it from that stream and store it in the underground. And in that sense, basically you get not just a carbon-free biomethane, but you actually get a carbon-negative biomethane. So it actually saves you CO2 by using this product. Same thing for sugar, starch, and crops. You can use these crops to ferment, and then you get ethanol. And from this ethanol process, you can capture CO2 and remove the hydrogen, and then you have an ethanol stream. And this is widely used in the world, mostly in Brazil, where they produce huge amounts of ethanol through this route from sugarcane. And there's also a new route, and that's down here, where you can use this also solid and dry biomass after pre-treatment and use it to make ethanol. And basically, if you look at the world, this is the low-hanging fruit for bio-CCS. It's a low-cost CO2 capture system to basically produce ethanol and remove CO2 from the process. Then we have the second route. I already explained that you can gasify material. You can also, of course, gasify biomass with oxygen and steam. And from that product, so basically a syngas, then you then produce in this part, you can use a water gas shift reaction and separate the CO2 from it using pre-combustion capture. And from then you can basically use that as a building block, as Dr. Arne explained, for the chemical industry. But you have then hydrogen, but you can also have a methanation step to produce synthetic natural gas. You can apply Fischer-Tropsch synthesis to produce diesel, gasoline, kerosene. And you can also have methanol synthesis, which is a very good building block for your chemical industry, but also for gasoline and dimethyl ether. So this is the gasification route. Then we have basically the power production family. So with gasification, you can also fire electricity plant by basically a natural gas combined cycle plant that produces electricity from your hydrogen flow that you produce from gasification, and you produce electricity and heat that you can use. You can also have this oxy-fuel combustion that I explained, so that you combust basically a very where you combust biomass with very high values of oxygen, nearly pure oxygen. You produce electricity and remove the CO2 and store it in the underground. And then we also have, of course, the route to combust biomass in existing power plants. Could be converted coal-fired power plants or co-firing of power plants. And then you capture the CO2 and you have heat and electricity production. And from these routes, you can just produce carbon negative electricity. So this is electricity that has a carbon emission below 0. Then we have the final family, and that's the industrial processes that are being fed by biomass. And from that, we could produce basically cement, for instance. We can apply it in refineries, in ammonia production, but also in steel and pulp and paper production. And these are routes also being explored right now, especially pulp and paper and the steel, the cement production in industrial programs in the world. So this will yield us carbon negative products, so carbon negative steel or cement in the end. So this is a graph that shows you a bit how much CO2 you can remove actually from the atmosphere by using these technologies. And I have to explain this graph a bit so that you understand. On this y-axis, you see the share of biomass you can use in a feedstock. So for instance, in a power plant, this is the big bubble here, it's a dedicated biomass power plant. It can use 100% of biomass. You can feed it with 100% of biomass. And then the x-axis shows you how much CO2 you can basically typically capture from such a plant. And from a large biomass plant, it can be 3, it can also be larger, but this is typically 3 megatons per year you can capture and store into the underground. So if there's 100% biomass, you can almost generate 3 megatons of negative emissions per year with such a power plant. And the bubble size also shows you basically how much negative CO emissions you can achieve. And if you then look at certain sectors, you can see that you can have the very big ones. So those are the power plants, but also synthetic diesel and Fischer-Tropsch production. These have potentials of about 2-3 megatons per year of negative emissions. And you also can see that you have the very small, or typically smaller factories of ethanol production and biomethane production. So they have potential, but they're much smaller in terms of how much annual CO2 emissions you can avoid with these technologies. Here we have a waste to energy plant that's basically making electricity and heat out of our waste. That can also give us negative emissions. Here down below, we have more the industry application, so cement production and steel, and it is lower not because of this that these industrial complexes are smaller, but it's lower because it's more difficult to fire those with very high shares of biomass feedstock. So that makes these plants attractive from carbon capture and storage, But for biomass combined with carbon capture storage, it's a little bit less applicable. So you can see a little bit lower CO2 emissions avoided in terms of negative emissions than for the other technologies. So now you have a bit of an idea of what kind of value chains could be existing and what kind of technologies could be existing. It's nice to also have a look at what really exists in the world. And on this map, I've used information from the Global Carbon Capture and Storage Institute, Global CCSI, where they report on basically the technologies that are being used. This is not biomass, this is just carbon capture and storage. And it shows you that there are around of 21 facilities around the world, and combined they capture 40 megatons of CO2 each year. And remember the number at the beginning of my presentation is that we need, at the end of the century, we need 16 gigatons. So that's a factor of a very high factor higher. After 1 gigaton is 1,000 megatons, basically. So we need to step up the game a lot. And also what you can see is that it's not well distributed across the globe. You see a lot of activity in the Americas. You see activity in Europe. You see some activity in Asia. But we need to step up to the plate to bring all this carbon capture technologies to the level we need for the IPCC scenarios. And then also what we need is basically carbon capture and storage projects with biomass if that scenario from the IPCC is going to make a reality. And what you see here is that there are some projects in the world now that use bioenergy combined with carbon capture and storage. They're mostly located again in America and in Europe. And the types of technologies that they apply is mostly by combining ethanol production, as I explained, from fermentation of crops. So ethanol production with CO2 capture. And the biggest one we have in the world is about 1 megatons of CO2 emissions being captured and stored. And that is in the US. But we also have some new projects and demonstration plants coming online that apply bioenergy with CCS, with industry and waste to energy plants. So we have basically a cement and a waste to energy plant ideas in Norway that are being explored. We have some capture plants also in the Netherlands that use a waste to energy plant and capture the CO2 from it. In the Netherlands, we also have an ethanol plant where you can remove the CO2 from, and it's being used in greenhouse horticulture areas. So there are some projects. In total, they're now capturing about 2 megatons per year. And the cost range is very big for these bioenergy CCS plants. The lowest cost range are for this easy to capture CO2 emission sources, so ethanol production, but also high purity CO2 sources. And the higher costs are for the low purity CO2 removal options. So think about also refineries, but also think of power plants. They also have a little bit higher cost than for ethanol. It can be tens of euros or tens of dollars per tons of CO2 captured, transported, and stored. So a poll question that's maybe nice to answer for the discussion round is what do you think is bioenergy potential for Indonesia? Yeah, so that's going well. Maybe we can come back to this in the discussion part. Then I can finish the last part of my presentation. Can we go back to the presentation, maybe? Yep. So I want to bring you some 4 challenges that we need to solve for biomass combined with carbon capture and storage. Basically, we need a regulatory framework. You need basically a framework that says we need to do this sustainable. The biomass sourcing should be sustainable, otherwise it's not going to be a sustainable source for our future. You need a financial incentive for the future. So you need basically money from the system that supports and has a financial incentive to actually store this CO2 coming from bioenergy sources. You need public engagement and political support, and you need build up this huge CO2 transport and storage infrastructure. And I have a small example of why this is very important. In this slide, you can see the total world land surface. So this is, let's say, the land surface of the world. And just to give a comparison, this red dot is the land surface of the United States in it. Then I have made a small bubble that says you the present worldwide land that's being used for agriculture. So this is the part of the available land that we use for agriculture. And this is so this blue dot is what we would use. So this is the bioenergy potential of 65 exajoules this is. And that's what we will need if you think about the scenarios of about 10 gigatons of CO2 so back towards the end of the century. So you can already see that you have to devote a very big part of your available land for agriculture to producing energy crops. So this has to be sustainable. It should not be an argument to basically clear out rainforest or a very valuable wildlife areas to produce energy from this system. So we should be doing this on land that is of marginal land, so it's of low value, doesn't have high biodiversity value. So we need to find a solution there. This is a big challenge. I think the biggest challenge for carbon capture and storage from biomass. Then we need also putting a price on carbon. Here you can see the countries in the world that are thinking or having a price on carbon, either a tax or a CO2 emission trading scheme. And without this price on carbon, it's never going to work. So there needs to be a financial incentive, and it has to also cover the whole world. Otherwise, you don't see this technology happening. Then also you need to have this politics and public perception in. Here you can see a small picture of how public perception could work against you if you're developing these kinds of projects. This is a potential blowout. It's of course not the truth, but it's being done by a graphical designer. But it could have important effect on how public looks at your projects. So you need to have the public and politics covering your back, basically. And then, last but not least, I already explained at the beginning of my presentation, you have to build this whole infrastructure from biomass production towards biomass conversion, carbon capture and storage, and transporting and storing it on the ground. And if you think about these big scenarios from the IPCC, you have to consider that you have to build these infrastructures that are now the same as for oil and gas production and distribution worldwide. So those are my key takeaways, and I'm looking forward to having a discussion on what's just presented.
Okay, thank you, Dr. Kornif, for the great presentation. I think we already have a lot of questions that is submitted through the Slido. So please, the committee help us to show the top asked question so that we can start the panel discussion for now. So for the while waiting for this question in Slido, I would like to give you some perspective about the current status of CCS in Indonesia for the speaker and also probably for the participants. At the moment, we have some CCUS probably only from oil and gas industry. So if you go to Subang, which is located in West Java. There is a gas processing facilities owned by Pertamina, the state-owned company, and the CO2 from those Subang field is captured by a private company to be sold as a industrial CO2 bottle source. But that's, I think, the only commercial CCUS application in Indonesia, which is coming from oil and gas fields. And the other development also mainly driven by the oil and gas at the moment. For example, a couple of companies, oil and gas companies in Indonesia, try to implement the CCS combined with the EOR because that's the low-hanging fruit, if you would say, the application that is at the moment economically feasible, while waiting the R&D in the other sectors to be developed. So yes, that would be the current status of CCS and CCUS in Indonesia. And also for another perspective, I would like also to give you some insight. It's quite different when we talk about CCS versus CCUS. If we talk about the CCUS that is explained by Dr. Katalhun, we understand that the CO2 will be used to be processed as a fit for another products. So the location may not be limited by a lot of constraints. But if we talk about the CCS, the storage, that means the CO2 has to be injected. That means now we're talking a very specific location, because we have to consider where is the closest available reservoir that can be stored CO2 safely. And Indonesia, I think there is some potential in that, because there is a lot of depleting oil and gas reservoir that is theoretically can be used as a storage for the CO2, either from CCS or bio-CCS, but still on ongoing development. So that's why we have the Center of Excellence in ITB, including the capture, the storage, and the transport to research those kind of things. Okay, so that's the information from me. So I think we will start with the top question. In a developing country like Indonesia, is it better for us to making current process more efficient so that the CO2 emission will be smaller, or directly implement CCU or bio-CCS? So, okay, I think I will give the opportunity for Dr. Katalhun first to answer this question.
Yeah, thank you very much. This is definitely a good question. So basically, we could translate this question into the idea on whether we should go for incremental changes to get some reductions on the short term, or if we should directly go into a solution that is in line with a global climate target. So as a reminder, if we would like to achieve the goals of the Paris Agreement, we need to go down very extremely in emissions. So if we just focus on fossil technologies, but improve the efficiency, we will never get close to even thinking about achieving the target. So much more emissions reductions are needed. Of course, it's good to make processes more efficient in the short term, but we need to start implementing the options that have the potential to gain emission reductions at the scale that is needed to achieve the climate target. So basically, it's good to do emissions improvements, but we need to start with options that will achieve our long-term target, because all the transition technologies, if they last for a short time, it will be a sunk investment, and so it depends probably a little bit also on how fast the improvements can be implemented. But it won't be enough to achieve the climate target.
Okay, I think that's a very good answer, that we have to think in the short term, mid term, and the long term. We also have to start think about short term, because we need some driver that accelerates this this progress. But I think that's a very good point that in order to meet the emission target stated by the IPCC, for example, it's also to start also developing the long-term project. In that case, the large application of CCS. I think, Dr. Cornif, if you would like to give some insight or additional comments for this question.
Yeah, maybe an additional. I much appreciated both of your answers, and I also think it's a very challenging question. It's very difficult to answer this, and I think what's very important is that, as already raised, you need to have this final incentive. So why would a country like Indonesia start investing in these technologies? You need to build up this infrastructure. You need to build up, in the case of CCU, this infrastructure for carbon capture utilization. But if you want to have this value chain for biomass with CCS, you have to invest in this value chains for biomass and bioenergy production with carbon capture and storage. So there's need to be this very sustainable financial incentive for the next 30 years to invest in such large plants. And that is truly the first challenge. So there needs to be political commitment on a global scale that trickles down to countries like Indonesia, but also in my country, the Netherlands, and in Europe and in other parts of the world, so that you can make this investment work. Then said, if these investments could work, then it is very important for Indonesia to consider whether you want to build off this biomass value chains, and what kind of biomass value chains would that be? As Indonesia is going to develop themselves as a biorefinery of the future, with this biorefinery centra that can ultimately produce energy, but also fuels for the other parts of the world. And then at a later stage, I would add then the CCS part, so the carbon capture and storage, because that's an additional and expensive step. So if the country would think about developing this, first think about, could you develop this biomass value chains on a sustainable way? And then at a later stage, if this global carbon pricing exists, that you can sell to the other parts of the world that you are storing CO2 for them, which is not possible. So that's a service you provide. Then add this carbon capture and storage part to it.
Okay, thank you so much for the answer. So I would like also to give comments on that because Indonesia is pledged to reduce the greenhouse gas emission by 29% in 2030. But if you look at the numbers at the moment, the focus of the government is not actually in the CCS sector, because we are, I think, like the fourth or the fifth biggest emitter in the world, but mainly coming from deforestation issue. So a lot of palm oil production, because at the moment we are the largest palm oil producer in the world. So to convert the land into those palm oil plantation, that's like the major producer of CO2 in Indonesia. And the other source is the peatland fire, especially during summertime. That also contributes to the largest CO2 emission in Indonesia. So that's why in the short to the midterm, at least to 2030, I think the focus of the government is actually to reduce the CO2 emission from those peatland fire and deforestation, and to improve the energy efficiency. And meanwhile, the CCS, we could say that it is in the consideration for the longer term, I think after 2030. So yeah, just as a perspective for all the participant and the speaker. Okay, so I think we can go to the next question. How can you deal with the industry retrofitting to implement the CCU process on existing plants? I think Dr. Ketelhun would be first opportunities for you to answer this question.
Yeah, maybe I can start with this. I think the first step that we need to do for the implementation is, first of all, identifying those plants and those opportunities where we actually want to implement CCU. Because our webinar today is on carbon capture technologies, on the use of the storage. But there are also other options we do to obtain renewable carbon feedstocks. And this is recycling. And we heard a lot about biofeedstocks. So you can go for either CO2 as a feedstock, bio-based feedstocks, recycled plastic waste, for example, or you can use fossil feedstocks, maybe as a transition, and still do the fossil-based CCS. And so in your playbook, you always have these different options. And the first step would be to understand what are the options where CCU is the most efficient one in terms of resource use and in terms of outcome. When we have identified these options, we need to understand that there are different pathways. I showed you that there's a pathway via methanol, and methanol allows us, it's basically a chemical where we can use CO2 and feed it into the existing infrastructure in the chemical industry. Because from methanol, we can use this methanol to olefins and methanol to aromatics processes to end up with ethanol, propylene, and the BTX chemicals, which are already produced in the chemical industry today. And all the further production steps in the chemical industry could stay exactly the same. And those methanol to olefins processes, for example, they already exist at a very large scale in China. They are currently using fossil methanol, which is very bad for the environment, but you could also use renewable methanol in these steps. Advantages, you can keep a lot of infrastructure. Disadvantage is we have seen that the efficiency is a bit lower. In other cases, we will need these CCU technologies, which can directly produce chemicals like ethanol, propylene from CO2. And this will be basically a replacement of existing infrastructure. And this will be much more costly in terms of capital investment. So this may, I can only assume here, depending on the financial incentives, that may be a later step that goes into the industry stepwise, because some plants will be faded out in the future, and maybe there will be opportunities. But I would say it's a little bit too early to say what exactly will be the CCS applications and the CCU applications in the future, and where are these other feedstocks more beneficial.
Okay, thank you. Before Dr. Koltnev, if you would like to add some comments, I just get some notification. Is it possible for you to turn up the volume of the mic? Because some of the participant is not able to hear the voice clearly. Okay, please, if you would like to add some comments about the retrofit versus the new build case.
Yeah, is it better like this without a headset?
Yes, much better.
Okay, sorry. Apologies for that. Maybe a small comment on that question. Indeed, it's very important if you want to retrofit existing industry, whatever that may be, if it's a power plant, if it's a chemical process, a refinery complex, you have to look at what kind of processes are there and whether you can actually build in this carbon capture facilities, whether you have space on the ground, whether you can disentangle the very complex exchange of heat and power on those in those industrial sites. So you have to look at it case by case, I'm afraid, and that's also what Dr. Kettler indeed explained. So that's very important, and it's also quite important that if you have a carbon capture installation installed on an existing site, you have to consider that you have some downtime of your industrial process as well. And that can be very expensive as well. Set aside the capital cost or other costs you may encounter. So for retrofitting, you have to look at the process and the site specifically. There's no other way, I'm afraid.
Okay. Yeah. Okay, thank you. So again, I would like to add some comments on this question. This is actually a very interesting question, and it's very dependent on the sectors that we are evaluating. Again, in Indonesia's case, I think it's the answer could be different if we're talking about the industrial sources versus the power generation. Why? Because I will start with the power generation first. At the moment, I think 70 to 80% of the electricity is produced, is generated by coal. And most of them are actually a new coal power plant. It's like built in the last 5 to 10 years to increase the electrification ratio of Indonesia close to 100%. Using that understanding, we have to be aware that the lifetime of a coal power plant is 30 to 40 years or even more. So the government will have a very big motive to keep operating this new built coal power plant. So that's why I think the retrofit issue is a very, very critical for this coal power generation in Indonesia. Yeah, as I mentioned, the last 5 to 10 years, the PLN, the state-owned company, built a lot of new coal power plants. So of course, later when the financial incentive makes sense to apply the CCS for them, of course the power generation will require a lot of this retrofit application. And for the industrial sources, maybe that's quite different because the amount of industrial petrochemical industry, I would say maybe not as much as in Europe or in China, for example. So maybe there will be a lot of opportunities for the new plant to be built directly with the CCUS in mind. So it's not gonna be the retrofit case in some of the other petroleum petrochemical in the sector, I think. Yep. So I think that hopefully answers the second questions. So we will move on with the next question about the bio-CCS. Currently, it looks very expensive. Shouldn't we focus on efforts to actually cut down CO2 emission? And if you don't mind, I would like to add a secondary question, a follow-up question on that question. What do you think the financial incentive required if we want to start applying this bio-CCS? So what would be like the minimum CO2 price or minimum CO2 tax that has to be used so that it could be feasible to be applied in a large application?
Yeah, it's a very good question. I think you have to look at them from the different processes I just rapidly introduced, where you can use bioenergy with CCS. There are some processes that have very low capture costs. So if you look at ethanol production, for instance, it has a cost of starting at $10 US dollar per ton of CO2 captured. And if you look at carbon pricing initiatives around the world, so let's take Europe, it's about 20 euros. So how much is that? $25 US dollars, $30 US dollars per ton of CO2. So you can already see that capturing CO2 from such process could already be valuable. There's already a financial incentive. So for some BECCS routes, like ethanol production, and in the future, I also think it's for biogasification with carbon capture and storage, that could have low capture cost and transport and storage cost. So it really depends on the technology route you take, what kind of cost you encounter. So that's first to note. And what could be an option for Indonesia could, for instance, be that you, these coal-fired power plants, in the longer term, you convert them also to co-firing biomass with it and apply a carbon capture and storage, this post-combustion capture technology to it. So in that sense, you basically retrofit your future power plants start from burning coal to burning also parts of biomass, and maybe in 20 years from now, make them fully burning biomass, and then you capture the CO2 from it and store it in the underground. In that sense, you gradually build your business case basically for BECCS. Of course, what's very important, and I don't know that for Indonesia, what is the cost of your biomass resource? For some parts of the world, the cost of biomass is very low, and it's sometimes also competing with fossil fuels. But it really depends on location. I think for Indonesia, coal is very low cost. So biomass resources is difficult to compete with that. So you need this additional financial incentive from a CO2 pricing mechanism. And that has to come from either political commitment on like a national level, or on a regional level, or on a global level. So that really depends on politics, I'm afraid. So that's a very important barrier also for BECCS or bioenergy with CCS. You need this political commitment for the longer term that establishes this CO2 price incentive for actually removing CO2 from the atmosphere. And if that falls down with the political uncertainty, that no big company is going to invest in that. So the key takeaway, there are already value chains that have profitable cost of carbon capture and storage. And certainly, if you go to 2030, 2040, when the CO2 price is going up, we hope, then these technologies can be profitable. But you always need this political incentive. And maybe one final note on the question is that why shouldn't we focus on cutting down CO2 emissions? But as you see in these IPCC scenarios, it's probably not enough to just cut emissions. Probably and most likely we need these technologies that actually remove CO2 from the atmosphere, like direct air capture, bioenergy with CCS, reforestation, or maybe we need them all. So that's why it's more of a policy, insurance policy to also invest in this technology.
Okay, thank you. Dr. Katalhun, if you would like to add some comments?
Maybe just a very quick add-on.
Yep.
Cutting down emissions is also very expensive in many cases. So we just did the analysis for the chemical industry, also for recycling, for the use of bio-based feedstocks without the subsequent storage. And what we also observed from these analyses is that we couldn't find many technologies which are at very low CO2 mitigation costs. So for the chemical industry, what we expect is that we have to pay quite a high price for CO2 mitigations that goes far beyond the current carbon prices, for example, in the EU here. So cutting down emissions, depending on the sector, also without the storage, can be very, very costly.
Okay. Okay, so maybe I just want to follow up on that question, and because we have to realize that the driver is not only about the economics, the cost, and so on, but we have to realize that the other driver would be the need to as much as possible reducing the CO2 emission, so that the catastrophic scenario of climate change will not happen. So using those constraints, so when do you see is the latest timeline for us to globally implement this large commercial of CCS, even though the financial incentive is still not there at the moment, but if we keep delaying this application in the next 10 years or even 20 years, the consequence would be probably even bigger in terms of the cost for the of the global warming in general. So any comments about what is the expected timeline for this CCUS and CCS implementation?
Yeah, maybe from the CCS part, there have been much scenario studies also by the International Energy Agency, and I think already 10 years ago there was this critical path of how many projects you would need now for 2020. To basically stay on track for in that 10 years ago it was still the 2-degree scenario. We're already now moving to this 1.5-degree scenario, and then 10 years ago they said it should be like 100 or hundreds of projects on carbon capture and storage now in 2020, and I just mentioned there are only a couple of them now. It's 20. So it's not enough by far, and certainly if you look at these scenarios by the IPCC, which are done by calculation tools, so you have to translate into realistic figures. If you want to reduce 5 gigatons per year with carbon capture and storage, either with biomass or without, you need to build massive, really massive industrial complexes and clusters and transport facilities to make that happen. So you cannot build that in 10 years time. If you want to have that in 2040, you should start building this now, basically. So the urgency is not enough. And I think the next 10 years will be critical to start working on this infrastructure. If we're doing it later, that means that we keep on emitting the CO2, and then we have to do a bigger job later in the century, which is maybe twice as big. So basically, the later you start, the more we have to do later in the century.
Okay, thank you. Okay, I think we can move on into the next question. Yep. So for Dr. Carnif, how can you deal with the piping of the CO2? As we know that CO2 is an acid gas that can corrode the pipe. So maybe it's from the source to the capture plant, and then from the capture plant to the injection site, for example.
Yeah, exactly. Now, there have been a very good question. Again, it's been a topic of research in the last at least 10 years, I know, maybe even longer. And basically, the short summary of it is I can share research later on in the chat or afterwards. But the short summary is that if you keep the CO2 dry, so if you remove basically the water content to very low values, then you're fine. So even if it's high pressure, supercritical CO2 that's being transported through pipelines, it does not matter that much. You get into trouble if you have high high water content in your pipeline. Then it can become indeed. Then it basically becomes an acid problem in your pipeline. So keep it dry. That's the short summary. And then you're fine. And there's a lot of experience with it globally with transporting pipeline safely. So not a big challenge.
Okay. Okay, thank you. I think that's a straightforward question. So the key performance is to keep it as dry as possible, so that typical carbon steel pipe could handle the job economically. Okay, yep. So the next question for Dr. Katelhoen. You talk about the options, the high TRL one, I think, to produce methane from the CO2 and hydrogen. So at what size capacity that we're evaluating this scenario? So how much CO production of methane can be produced, let's say, from one typical plant, and what would be like the possible scenarios to use those methane? So this is from Amin, who asked whether it's viable to be used as a source for a power plant.
Yeah. That's a very good question, and I have to admit I don't know the exact figures of how much methanol you can produce from depending on the plant size of the coal-fired power plant, but you basically can calculate the C content from the structure of the methanol, but the input. But an assessment that we did is to try to answer the question, how much CO2 will we have from concentrated sources in the future and today, and will it be enough to satisfy the entire demand? And we did this assessment for Europe, but I would expect it to be very similar in many areas of this world. And what we figured out is that nearly all over the continent here, we have enough large-scale power plant which produce CO2 at a highly concentrated rate to basically provide the C feedstock, and that would be needed for the entire industry here. This is for today. So as a next scenario, we followed the decarbonization scenarios of the International Energy Agency. and looked into decarbonization options of existing applications, because in the future there will be less sources for CO2 that we could use for CCU. And also here we figured out that we don't expect there to be any shortcut in CO2 due to two reasons. There will be some remaining sources, and there will also be in the future bio-based sources where we can still capture the CO2. So basically, the sources are not the problem for CCU. There will be enough CO2, and also in terms of the transportation, we should not forget that CCU is slightly different compared to CCS, because in CCS we inject larger amount at a central space. CCU, we can choose a plant location a bit more freely and on purpose put it to the area where we have basically a CO2 source right next to it, and enough of the renewable energy that we might need, or the other feedstocks in the location. I'm sorry, I see my video is turning off and on again. I hope you can still hear me well.
Okay, so maybe the follow-up question would be, what do you think is the utilization of this methane production? Because if the methane itself is used as a source for power plant electricity generation, without integrating it with how the CO2 flow works. I mean, because the power plant also will emit CO2. If the methane is used as a source for electricity generation, it will be burned, and then the electricity is produced, but CO2 is again produced from the power plant. In that case, will the CO2 emitted from this new power plant directly goes into the methane production from the CCUS, or there will still be emitted CO2 to the atmosphere?
Okay, yeah. So for the CCU that based methanol that I was talking to, I wouldn't generally recommend to burn it for electricity production, because we needed electricity to produce this methanol. So basically we would have all the conversion losses. Having said that, of course, we can still use the methanol as an energy storage. So in some cases it makes sense. But where it is more valuable are other applications. I showed the chemical industry, so the carbon feedstock. We will need it in the future. And it is not possible, like in the energy industry, to do this without carbon, because the carbon is what we touch when we have our computer in our hands. So we will need a feedstock for this. It is very valuable. And there's some work being done looking in CO2-based fuels, which could be very interesting for heavy-duty vehicles, for example, because there we expect that this will be more difficult compared to battery vehicles. There are CO2-based applications for aviation fuels, and I believe that the feedstock area and the areas where we can't directly use the electricity will be much more promising, because we need to remember we use the electricity to produce a fuel. So it's not we had electricity before. Okay.
Yeah, thank you. I think that's a very good perspective. That maybe that's because the nature of developing countries like Indonesia, where we have gas resources like methane, then the first gut would be to produce electricity and so on, because the industrial petrochemical industry is not as developed as the other part of the country. So that's where we have to think for the future, to give a more added value for the methane itself instead of burning into electricity. Now we get methanol or even other derivatives like acetic acid and other derivatives. So I think that's a very good insight. So for the next two questions, I think it's quite similar, so we can combine it all together. Will there be any drawback in injecting CO2 back into the earth? and what's the side effect when it's injected into underground. I know that both of you are not the main area in this storage, but maybe some of the participant has not had any clue about how the consideration of this injection in the underground. So maybe just provide some a brief insight about this question.
Yeah, so it's a very good question, and the projects that are storing CO2 typically also very well monitor what happens in the subsurface with the CO2. So, for instance, in Norway, there's an offshore CO2 injection plant already for running for a decade. The ChEminar project, you maybe well have heard of it, and it's injecting CO2 into an aquifer. So that's a water-bearing layer in the subsurface, kilometers depth, where you inject the CO2 in. And as I explained, you can also inject it into an empty gas field or an empty oil field. And basically, you have to think of several things you carefully need to monitor when you're injecting CO2 in the subsurface. You have to be very well sure that the CO2 that you're injecting is staying there. So you have to have this layer above your reservoir where you're injecting it. It should be a good like a cap on it. It's a cap rock. So that should be a bit of the earth that really captures the CO2 well, and so that it stays there. So that's a very important thing you need to check before you start injecting, and also you can monitor that partially by during the injection. So that's a very important thing. A chemical process that is maybe interesting when you're injecting CO2. So if the pressure downhole is pretty low, for instance, when you have an empty gas field, and after production you are storing CO2 in it, is that if you inject a high pressure CO2 in it, you get like expansion in the bottom hole. You can maybe expect that, and due to the Joule-Thomson effect, you get cooling in the reservoir, and that's something that could be a challenge, and that's now an important part of research, how to prevent this and how to work with this when you're injecting CO2 in empty oil and gas reservoirs. So you have to check the reservoir before you're injecting, check the reservoir, basically the layers above your reservoir carefully before and during injection. And you have to monitor the CO2 with, for instance, like seismic surveys to see whether the CO2 is staying there. And then a very important part is then you have to check whether your well, so it could be an existing oil and gas well or a new well, is built up the good materials so that the CO2 cannot leak past your well to the surface again. So I think those are the most important aspects to think about CO2 injection. But this should always be looked into perspective, because CO2 injection is already being done in the oil and gas industry because of enhanced oil recovery, for instance in the US, but also other countries. It's been done for decades already. So there's a lot of experience with injecting CO2 in the subsurface. And there's also a lot of injecting CO2 in the subsurface for actually storing CO2. So yes, you have to very carefully check your subsurface and monitor what happens. But if you look at the project right now, there's ample experience that we could do that safely.
Okay. Any comments from Dr. Katalhun, if you would like to add something?
There's nothing to add from my side.
Okay.
Thank you.
Yep, that's fine. So maybe another session if we need to invite the expert on this CO2 storage about how they properly select and model the injection selection. Some of the key important features already mentioned by Dr. Cornif, that it has to be able to maintain the CO2, keep in the underground for, let's say, 100 or even 1,000 years. So we don't want to inject the CO2 and then it keeps leaking to the surface, to the ground, above ground, and then the communities close to this location will have some complaint because it's unsafe for them and it's affecting their environment. So that's why that's a very important step in selecting the injection or storage site of the CO2 well. Okay, I think we can go back to the Slido. So let me check the next question. Okay, so the next question would be, are there any drawbacks on CCS and CCUS and bio-CCS implementations, and what is the strategies to compensate the drawbacks at the moment?
Maybe I can start for the CCU part. I think for CCU, a drawback of many of the ideas that are out there is the electricity demand. So as I showed you in this presentation, CCU at the moment requires a lot of low carbon electricity. So one very important stream of research is the question how to bring down the amount of renewable electricity that we need. This is on the one hand. But having said that, on the other side, there are also CCU technologies which do not need renewable electricity, for example, CO2-based polymer, because they react with another high energy reactant. So those technologies will not have the same drawback, but I think most of the CCU technologies do have this huge demand. And this drawback in terms, or drawbacks, this characteristic, I would say, of these technologies translate in also the outcome of the financial calculation for these technologies at the moment. CCU technologies are not in all, but in very many cases more expensive compared to their fossil-based counterparts. So bringing down the cost of carbon capture and utilization is essential for the market entry, together with stable and sufficient political incentives to improve the finances of these technologies. What we have to keep in mind is that we have been optimizing our fossil-based technologies for decades. They have been much more expensive when they entered the market, and there will be a strong learning curve also for the renewable options, so the cost will go down. We saw this for renewable energy. We will also see this for renewable feedstock applications in chemical and energy industries.
Okay, thank you. Any comments? Yep.
Maybe to add upon that, I think for carbon capture and storage and bioenergy with carbon capture and storage, one of the major drawbacks is if you build these projects, they're often very big. So you, in terms of dollars, it's a big power plant with carbon capture and storage added to it. It easily is $1 billion, easily. So you need massive investments for 30 years ahead to make this financial incentive or this financial investment work. And if you compare that, for instance, to solar panels, which you can buy by piece, which are just a couple of $100 per piece, but they have very different dynamics if you look into the future implementation of these technologies. So a very big disadvantage of BECCS, I think, is you need to build this massive infrastructure. I've said it once, I've said it again, which needs a very high investment cost. And so you need to have this stable investment security by political and regulatory framework that is sustainable and reliable for a long term. Otherwise, it's not going to work. And specifically for BECCS, so for bioenergy, you need to have this sustainable source of biomass for the longer term also. So that could not be by removing rainforest or something else. That should come from a renewable source of biomass for the longer term. So again, for this 30 years ahead, that is competitive with other sources of energy. I think those two things, it's very big, very high investment, with strong political support needed, and you need this biomass sourcing stream to be sustainable for the longer term. Those are the most important ones, I think.
Okay. I have a follow-up question on that because, I just think one possible sectors in Indonesia for bio-CCS that may not have been looked as much as the other As I briefly talked about it before, that we are at the moment the largest palm oil producer in the world. So, and a lot of CO2 emission coming from that plant, including the deforestation, but also there is another source called as the liquid waste called as palm oil milling effluent. In the most conventional process, this liquid waste is just dumped into the open pond, and then the CO2 and the methane will evaporate to the atmosphere. The problem is it's a small scale comparatively to the other power sources, but it's a lot of palm oil milling effluent. I think there are at least 600 palm oil milling effluent plant in Indonesia, and that accounts a lot of emission. So what do you think about this? Because there is an ongoing development, I think, in the last 5 years, where this liquid waste from the palm oil is not dumped to the open pond. Instead, it is sent to the anaerobic digester, so that the effluent now is converted into a biogas. Then the biogas can be sent to produce electricity or to be used as a liquid fuel, and the CO2 is not directly emitted to the environment. Now maybe we can combine this concept, the biogas power generator, the small one, with the bio-CCS, if there is some close CO2 storage within proximity. So any comments on that?
Yeah, not being hindered by knowing the details. So I just thinking out loud here. I think centralizing the streams would be almost a no regret thing, I think. So bring these effluent streams together so that you can build a sizable plant that converts this effluent into a valuable product. And that could be indeed fermentation to produce biomethane. And as I explained in one of my slides, you can capture this CO2 from biomethane processing. And if that's big enough, you can have economies of scale, so that you have like a big biomethane plant with based on digestion, or maybe in the future even gasification. And then from those plants, you can capture the CO2 at fairly low cost. It's doable. It's not as low as for ethanol production, but it could be cost competitive. And then if you do that in an industrial cluster, that effluent combination and processing, then you can make use of the CO2, as Dr. Krettelhorn also explained, or maybe in the future, if there's a proper financial incentive to store it in the underground. But centralizing it and getting economies of scale is quite important for CCS to bring the cost of transport and storage down.
Yep. Okay, thank you for the comments. I think because the time is up, so that's it for the Q&A session. So I would like to thank Dr. Krettelhorn and Dr. Cornif for your presentation and also for your insights on this discussion. I think it's very fruitful discussion and gives a lot of new information to the participants and a new awareness. I would hope that it's very important for us to consider or to develop the CCS technology in the near future, as the challenge of mitigating the global warming becomes harder and harder. And Indonesia has a role on that purpose. We talk about the potential in biomass sector, or even in the power generation sector, and in the CCUS, in the industrial source. So I think at least now we need to keep spreading this awareness and think holistically that it's not only about the economic driver. Yes, we need the financial incentive, but we also have to fight for that financial incentive, because it's very important. If we keep it as business as usual, then we will have a greater problem in the future. So as a concluding remark, I think Dr. Krettelhorn already talks about the screening models developed to help us to select which industrial sector would be more prioritized to implement the CCUS. And I think that's that kind of screening model is very important because we have some limitation on the budget and so on. So we need to be strategic with this initial implementation. And I think from the presentation and Dr. Cornif, we heard about the bio CCS and how its unique object position in the CCS, because it could reduce negative emission. So if we're talking about the conventional CCS, we just talk about the avoided CO2 emission. But now if we combine it with bio CCS, we can achieve the negative emission because we produce it from the carbon neutral sources, and then we still keep capture and store those CO2. So that's why it can be accounted as negative emission, which is very important if we want to achieve the target specified by the IPCC. So I think that's some of the main conclusion from this discussion. So thank you so much for the both speakers and the participants. I will conclude this webinar and return it back to the MC. Thank you.
Thank you very much.
Okay, so we have come to the end of this webinar. First of all, I would like to say thank you to Dr. Arne Kittelhun and Dr. Joris Korne for giving the time to share all these valuable insights and meaningful knowledge to all of us here. And we also would like to thank Mr. Anggit Raksajati as the moderator of today's discussion session. Lastly, we would also like to thank all attendees for coming to this webinar and participate in the discussion by giving questions in the Q&A session. Before ending today's event, I want to briefly explain and refresh your memory regarding the upcoming AISC competitions and the other upcoming events that is held by AISC. So as I have told you in the beginning of this webinar, there will be a paper and poster competition, and it will be closed. The registration will be closed by the 29th of November 2020. If you join the competition, you can win a total prize of $1,400 US. So mark the date on your calendar and don't miss this opportunity so that you can win the $1,400 US. But besides that, the finalists will get a one-on-one mentoring session with curated sustainability experts. What a cool opportunity, right? So don't miss this. The first winner of the paper competition will also be attending the IT Annual Student Conference 2021. And please note that if you register the competition between before the 14th of November, you will get a chance to get a free admission to academic writing and data visualization one-on-one workshop held by the World Resources Institute Indonesia. Regarding the academic writing and data visualization one-on-one workshop, it will be held by on the 14th November 2020. And for those of you who didn't get a free admission, please don't worry because you can register by paying only 20,000 rupiah, which is very cheap. It's a very good investment for your future paper competitions and other conferences. So for those of you who want to join these competitions and you want to keep up with the information, please follow our Instagram account and stay tuned. Finally, to get your e-certificate and bonus notes of today's AISChat, fill in the feedback form. So you need to fill a feedback form by the end of this session, and there will be we will send you the link and the corresponding password for the feedback form. And okay, so for those of you who have filled in the feedback, thank you and see you on the next AISChat 4. I would like to thank again Dr. Aina Ketelhoon and Dr. Joris Kornhef and also Mr. Anggit Raksayati to have joined this webinar session and share your meaningful knowledge to all of us. So see you on the next event. Today's event wouldn't have been realized without the help of our sponsors that are PT, that are the EMI or the Energy Management Indonesia and the PJB. So we would like to thank these sponsors, the PT Pembangkitan Jawa Bali and Energy Management Indonesia, and also the WRI, the OPA, and all of our media partners, because without all of these stakeholders, we wouldn't have realized today's event. So thank you so much. And I would like to remind you again, please don't forget to register on the AISC competitions and the conference day in the upcoming year. See you on the next AISChat.